Well, what about if you start locking? Well, locking is a very quick operation, it is true. Especially if you are in a situation where you are not going down to kernel threads, and you can log at the initial level. It's quick, and especially if you have stuff like bias locking, it's even quicker. So it is not a big deal. And you can say that, yeah, it's still probably quicker. But then, what happens when you have many threads? Well, now you have to request the log. You are in a thread, you go for the log is busy, someone else is using it. What happens to your thread? Suddenly it's bigger, so the memory has to be copied. All the memory is local to your thread has to be copied somewhere else, and then you have to wait. And you may have to wait, and you may have to wait, and you have to wait. And depending on how the code is implemented, you may have a deadlock. Or you may not. Suddenly, you don't know how much time this operation is actually going to take. Whereas if you are in a immutable situation, you pretty much have a good idea how long is it going to take to copy whatever you are going to copy. It's a much more stable situation. So in general, we tend to prefer immutability because it gives us a much more stable platform. Not just because, immutability, we will have to explicitly synchronize only bugs. Is that performance is much more average. So in the end, immutability leads us to making it very easy to reason about what our code is doing at each specific moment. It is much easier to test. We don't have to try to replicate the 1 in a million situation where this value behaved this way and there was this weird interlocking of threads. That is incredibly difficult to test, but it is also incredibly difficult to debug after the fact. How do you even, after you only have logs from last night, how do you even reason about what happened there? It's incredibly difficult. It's incredibly difficult. And something that I didn't put there is that even though performance for immutable data structure is traditionally worse than for mutable data structures, there's been a huge amount of effort made in the last 15 years. And if you check the data structure that I use, for instance, in Clojure or in Scala, even though they are immutable, they are immutable in a clever way, so that they only modify the part, so they only copy the part that's a part of the area around what is modified. But that's for another presentation. I'm going to do that here. So in the end, immutability, if you intend to work in a reactive way, should be very important. It doesn't mean that you cannot have immutability. It doesn't mean that if you have a specific path of the code that you know that is very hot and that has to be executed in the absolute utmost speed, you can use immutability. You can use something like a reactor or the disruptor, or you can use a variable queue or whatever. But as a default, you need immutability, and you have to have a reason to use immutability. Traditionally, it's been the other way around, because traditionally we were not dealing in this kind of system with zillions of users. So let's talk a bit about responsiveness. And I don't want to talk a lot about responsiveness because to me it's the least interesting. Basically, we want our systems to reply in a timely manner. Basically, we don't want timeouts. But also, we don't want spikes. The idea is that we want to have a good model of how long this operation is going to take. I send a REST request to that server. I know it usually takes 200 milliseconds, fine. I can tune it in a much easier way if I know how much, if I have a clear idea how long it's going to take. So in the end, it's not about being the fastest. It's not about being right now being the one that has the answer. It's about being flatter. So here, for instance, the blue service, it's easier to work with it because the orange has crazy peaks. It's very hard to work with a system where you can have that kind of crazy peaks because, well, where is the timeout? You know that if that peak is something that you are expecting, the timeout is going to be way over the limit. It's not going to give you very good information. Whereas in the blue, you can set a timeout that is very close to the average that is giving you, you know? So you can set the timeout that this may be around here, and you know that the timeout is going to be good. Whereas in the orange, if you get this kind of things, your timeout probably needs to be around here-ish, maybe. But that's a problem because the timeout is much bigger than what it probably needed to be if the service was much more stable. Also related to this, to responsiveness, there's a lot of documentation on what kind of data to measure, what are the good indicators. You know, you don't measure averages for this. You measure 99% and that kind of stuff. But I'm not going to go into that because that, to me, that's the least interesting part of this talk. And I want to go into code examples at the end, if we have time. And a much more interesting aspect is being resilient. And resilient has very many different aspects, but this is probably one of the most important assurances that reactive programming gives you, is that your service is going to be there. No matter what it happens, your service will have ways to handle errors, to handle disruptions, to handle node design suddenly, but your system is still going to be there. Or at least it's going to give you the tools to handle these kind of anomalous situations. So this is something that you find that when you're dealing with this is something that a lot of people are not used when they haven't worked in something like server-oriented architecture, or when they work in a single node, in a single stable server, and they develop a heavy Java enterprise application with a single source of truth database and that kind of stuff. It's that everything can fail, anything can fail, anything will fail in your application. Your code will fail in unexpected ways. Your hardware will fail in unexpected ways. If you throw enough nodes to your system, maybe your hard drive, the specific model you're using, only fails once every 5 years. But if you use, I don't know, 500 of those hard drives, you're going to have a failure every 5 days. More, a little less, but that fails. The network can fail, you know. Sometimes a network administrator goes and changes the routing in a router, and suddenly half of your nodes don't see the other half of your nodes, and see that. Everything can fail, so you need to somehow account for all these possible failures, because otherwise you are going to get a call at night, at 3 in the morning, and hey, something is broken, and it's untenable. So one very important thing when you are working with this kind of system is that you have to accept the failure. It's inevitable, and you have to work with it. By the way, that's my cat. Sometimes fails. He's actually comfy in there. It looks painful, but he's happy. So it's very important to identify that the errors are also part of the domain model of your application. The possible behavioral statuses that your application can be in, that includes the errors. If you use Scala before, or some other languages like Haskell, you're probably used to what some people call algorithmic data types, like for instance tries, where you, in the same data type, encompass the success of the operation or the failure. Well, the idea is something similar to that. Another very important idea is to be able to bucket your different subsystems. So make sure buckets are the different parts that are inside the big box, so that if one of them is breached, the others don't see. And it is very important to bucket your system. You need to know that the database can go down. If the database goes down, what happens with the rest of nodes depending on the database? Can you still operate? Is there any way that you can still serve your users, even if it's in a reduced way? But that's highly dependent on your specific application. And in the end, no single system should take down your whole app. There should not be a single guy that controls everything. That should be done away. If you work with microservices, you already know this idea. And in the end, this is something that is taken from that kind of philosophy. Nothing is that important. Nothing should be as important as your application dies completely. Even if you are just serving a 503 or any other error that you want, nothing should make you start returning for the users. Something that a lot of people coming from imperative languages assume a lot when they are implementing their system is that the global state exists. You know, that they are this omniscient I that sees everything, and that you know everything that is going there. At least everything is, it's not that you know everything, but everything is knowable. That there's the possibility of knowing everything that goes in your system. But suddenly, when you are splitting your system into different nodes, that is no longer true. There's a branch in logic called epistemology. And one of the problems in epistemology is the two-general problem, or the Byzantine general problem. You probably heard of it if you read about this kind of algorithms. And what it tells you that in a distributed system, where you are assuming that you can have failures in the middle, you cannot have a single source of truth. You have this node here, and you have this node here, and this node suddenly says A, and sends the value A to the other system. You know that there is a moment in the middle where the system, in my left, doesn't know what this system sent. Global state does not exist anymore. So whenever this guy receives the A, what happens if the system has generated B already? Each one of the systems has a subjective view of what the world is. There's no global state. And that's why I say that it's a lie. It's something that we should do away from. We are not omniscient, and we cannot expect to have a single source of truth. I've seen a lot of systems that try to be reactive and fake it by creating a layer, which is usually a database, saying, well, this is our source of truth because everyone communicates through the database. Well, you just broke your system, and it's no longer reactive, because if your database fails, you are failing the guy on the right. It's no longer resilient. You may shard your database, and there are a lot of techniques. But still, there's a single guy, a single system that can take down your whole application, because you try to be omniscient, you try to use a single source of truth. Your code should be happy enough with having something that is not completely true. Even if the idea that it has of the rest of the system is partial, it should be happy enough. That leads me to the cat theorem. Who here is familiar with the cat theorem? So everyone. You know, it's like you have three. You have consistency, availability, and partition tolerance. You sometimes change. You have to pick two. It's very well known. As soon as you have a distributed system, a system that is composed of different subsystems that may be in different areas, you cannot have the three of them. You cannot be consistent, so you cannot have to be consistent among all the subsystems. You may have availability, so if someone dies, you're still available, or partition tolerance. You are resilient, and somehow your nodes split into two. But again, this is another lie. This is not true, because anytime that you deploy, anytime that you do anything, you are deploying it onto a network. And the network is going to be split eventually. That always happens. It's unavoidable. So partition tolerance, out of the two that you can pick, it's already picked by you. It's already picked for you. You need partition tolerance because you know that this is going to happen. And it happens all the time. No matter how much money you throw at the problem, you are going to have partition tolerance. Unless you're real. So you need to pick either consistency or availability. And you need to know what it means. If you pick, for instance, if you pick consistency, I want to be consistent. I want to be partition tolerant, so my network can be split, it will come up, but I want to be consistent all the time. I want to be AC. It's like I'm in a finance house. I want to be consistent all the time, and I know what's the data I have in there. Well, it's fine, but when you have a partition tolerance, you cannot have consistency anymore. If you want to have consistency, the only thing you can do is die until the network is no longer broken. So you lose availability completely. If you want consistency, you lose availability. There's no other way around it. But if you go for the other option, it's like, well, I always want to be available. I always want my service to be there. I always want it to return with the knowledge that it had until the network split. Well, in that case, you may not be consistent, and you may get a value that is not the actual value that you were expecting. But at least you will always be there. And most of the technical solutions you have on the internet rely on a solution of the cat theorem. It's more or less like this. So, for instance, if you go to Google Docs right now, and you get disconnected from Google Docs, it's still going to capture your key stores. And what happens if you are working in a document at the same time that someone else is also working in the document? You may be disconnected. So the system may still capture your key stores, and it will display you what the state of the document is in your disconnected state. And when it finally reconnects with the rest of the network, well, this may change a bit. It may do a merge, or that's a decision for whoever implements it. So, in general, what most people try to approach is something called eventual consistency. Is that if there's no new update into some specific value, after some period of time, you will get the last updated value. There's an acronym that was published in a paper 2 years ago by the guy that coined the term cap theory. It's called Brewer, which is basically a very low state eventual consistency. Your system, if you use an algorithm that gives you eventual consistency, it's going to be consistent eventually. It's much more restricted insurance than traditional AC, but it gives you these capabilities. So, if you're interested in this kind of algorithms, these are some existing solutions to this problem. I guess here, who has read Paxos? Good, like 6 people. Who here has understood Paxos? What? Liar! Really? Okay. Some people don't understand, I don't. So, Paxos is a very, very complex consensus algorithm. It's difficult to understand consensus algorithm. So you have RAFT. It's another consensus algorithm. It's a very funny white paper because they actually published a study they made with the students in the university, and they gave them Paxos and RAFT, and then they queried how easy do you think it was? Because one of the goals of that algorithm was not just being correct, but actually being simpler to teach than Paxos. And it's a bit simpler. And you also have things like CRDTs and primitives to do this kind of consensus stuff. But I'm not going to go into that in this presentation. So I'm going to talk now about message-driven, which is what I guess most of you came here for. You didn't come for the philosophical, yabbering about philosophy and how to do this stuff. Message-driven is what underlies reactive programming. And message-driven is something specific called message, not events. There's a slight difference in an event and a message. A message is something that you give to someone that is an active act. Here we go. This is what I'm giving you. This is the letter. Now you act and do whatever you want. Whereas an event usually has something attached. This is the event, a click. This is the callback that is associated to the event. There's not a big difference, but it's a slight metaphorical difference. And in fact, this is the second version of this diagram. In the original version of the diagram, the Reactive Manifesto paper, it was event-driven. They changed it. Just because of that tiny difference. So I'm going to talk about what kind of message-driven we are looking for. We are looking for asynchronous message passing. So basically, we don't want to block. We want to be able to tell someone else in our subsystem architecture, this happened. It was like that. So here, for instance, I have an example in Scala. As I say, don't write Scala like this. If you ever write, see, even IntelliJ is freaking out here. don't write 3 times a number. So, for instance, here I'm generating a random ID. Then I'm constructing an order message object here, second line, and then I'm sending a message. So this bang means send the message, right? In act. I'm sending a message to the logger actor with a string placeholder, whatever. That doesn't work. I don't care how logger is going to handle that. I don't care if logger is not even listening there. I don't care if logger exceptions. I keep going. And then I instantly, as soon as I finish that operation, I go to the next one. Order engine, and then I send it the order. And again, just as before, I don't care about what happened. I don't care about order engine replies. It doesn't mean that I'm not controlling the errors, but at least in this code, it's just going there and I just keep processing. And then I find the ID. As you can see here, at no moment I'm blocking. There's no need for me to block. It's quite transparent. Another important idea in messages is that they have location transparency, right? So it doesn't matter when I send a message where the receptor is. It should not matter. Because if you want to use the possibilities of the cloud and I want to suddenly start, raising nodes, my code, my specific business code cannot start worrying about, okay, but where is this guy? Where is this located? This is located in this warehouse, this is located in this other one, this country. You don't really care. So you need something like location transparency. Just send the message, it will arrive. You are not interested in how it is going to be routed there. And in this example, I'm talking about actor ref, which is a way that in ACAP you abstract an actor. Even though you are instantiating an actor is a class that you implement, that you implement in a specific way with specific methods, local state, whatever. What ACA is going to give you is an actor ref. And the actor ref is just, only one method there. So it has more methods, but basically just a mechanism to send messages. It's like a mailbox. You're just getting the mailbox to that guy. And that is the only way that you are going to communicate with that guy. And since you no longer know about this guy, you no longer where it is located, you no longer know how it is implemented, you no longer know what methods it has, well, finally, you get the freedom from having to know how to operate with this other actor. Who cares? It may be the other corner of the world, for all you know. The system, the underneath system, is going to care about that. And all that logic, well, the business logic is completely free. You don't really need to care about that. So in the end, you don't care about this or this. This is a great advantage. It simplifies your code enormously. Okay, so in the end, when you are working with the states, there are 3 concepts. You have a state, you have a message, and then you have the state after you process the message. This is basically a state machine. This is a very good way of modeling reactive systems are state machines. State machines are very powerful because they are very easy to reason about. These are my states. If you try to keep them simple, they are simple. They can be a bit difficult. You can very easily test them because you have specific situations. You have something that is spec. You know that you are in this state. You know how do you get into the state. You know how to get out of that state. You know which messages you are handling. They can be fully specified. You can have a document saying, this is what I'm accepting. This is the state I'm in. This is what I want to accept. And something that is not reflected here, but is also quite interesting, is that state machines can be automatically tested for correctness. There are some projects for testing state machines, and they are using the NASA and these places to make sure that what they are implementing for sending robots to asteroids actually work. So I'm going to talk about how we can implement message systems. And in particular, I'm going to talk about different approaches that different technologies have And I want to talk about the advantages and disadvantages, because even though this is the only, so the message driven is the only part in Reactive Manifesto telling you how to build a system. It's not actually telling you use this framework or use this other framework. Depending on what kind of technology you're using, you can use something or something different. I need to start talking about the event loops, because everyone who's familiar with a browser, and I think everyone is familiar with a browser, knows what an event loop is. It's basically a way of having non-blocking concurrency in a language or in a platform where you only have a single thread, right? So you just say, well, when this happens, call this code, right? And then you have a queue, and then you have a single thread that is going to be the populated things from the queue, populating events, and then executing code as it is processed. Typical example is the hello world code for Node.js, and they want to go for something even a bit more complex. It's like, well, you create server, and whenever you get any request, this callback is going to be executed. It's extremely simple, it can run in a single loop, it will be iterated. Everyone is familiar with it. It works, it has its problems, but it tends to work pretty well. There's a problem though, in that it is actually quite difficult to extend to bigger scenarios. What happens when you have a relationship between events for your event loop? So for instance, this is a very silly example where you are reading from a file, and then when you read everything from the file, you write to a file, you don't blank, and you don't want to go into those two operations. Well, you have to nest the second callback inside of the first callback. There are solutions to this. You can, put the inner callback outside and into a different function, and we call this a bit nicer. But it is true that it grows very quickly. It grows very, very fast. Here I just added another callback for logging when the write is finished, and it starts growing to the right. It's a very good phrase. I really love it. But this is where code marches to the right faster than it moves forward. You start getting callbacks. And not only that, it's also that if you have all these callbacks, how do you handle the errors? Can you quickly identify the error code in there, the error handling code? It starts to get a bit iffy. And here at least the indentation is helping, but sometimes it doesn't. And very quickly you end up in a callback hell situation. You start having callbacks inside of callbacks. Where do you end? Right? It's hard. I'm not saying it doesn't work. It does work. It actually works. It's a good model for where it is. But it has these problems. And one of the main solutions could be, for instance, futures. Futures is basically a read-only value that's the result of computation. This is an integer, and you are going to get an integer eventually, right? Features are very powerful. Features are promises. So they are a great solution because you are not blocking anymore, right? You know that features also give you a bit more knowledge about the computation, because they either give you the value or the failure. So now, if you are using a type system, you can do a bit more intelligence in there. And also features can have a timeout. You can say, well, wait for this feature, but only wait for, 100 milliseconds. Which is the way I've seen a lot of people handle features, which is like this. This is bad practice. Blocking, right? Wait for this feature for 100 seconds. Well, you are trying not to block, and you start using features this way, well, you're defeating the reason why you started using features in the first place. But I've seen many places, I've seen many people, I've seen a lot of code where the developer was justifying saying it is necessary to do so, and pretty much nowhere was needed to actually do it. Features can be processed, can be developed in a much more consistent way with the rest of the system by doing stuff like, for instance, processing as a callback, right? Here we are processing the complete callback for the future. As it's a pattern matching in Scala. If it's a success, you print the number that you got. In here, if it's a failure, you print the error that happened. That's nice. I mean, we're in the same situation as we had with the callbacks, in that what happens if you want to call another future inside that future? Well, again, we are in a bad situation, but at least it's a possibility. In Scala, and in some other languages, we can also process futures with a map. So here, for instance, we can do a map operation in the future, and it is treated in a similar way as if the future was a collection. So when this future actually executes this, it's going to run this logic. You can, I think you can specify, here it's inclusively specified, you can specify a timeout, and the map operation will time out if the future has to finish. Another very, very interesting capability in Scala, and that is not in every implementation of future that you can find out there, that you can compose them functionally. What we have here is called a for comprehension. And what you are creating is that out of two futures, so a feature of an int and a feature of a string, with this for comprehension, you are creating a tuple. You are creating a feature of a tuple of int and string. So no longer you have to deal with the two futures, you are getting one future out of the two. And why are we interested in that? Because if we do this, we no longer have to implement a callback inside of a callback. We can do this, and it's the same behavior with a much nicer code, easier to read, also much easier to add additional logic. So for instance, here in this specific configuration, we are only doing this operation if the number is positive. It's a great solution. It's not perfect. This is so functional composition is nice if you have a small amount of features, but when you have a row, you have difficult error situations, as in I want to compose n for five features, and I want to treat the errors in a different way. That is a bit more iffy. It doesn't work as well. So in 2005, I think it was Sergio Rodríguez started Reactive extension for .NET. I'm sure some of you have heard of it. It's basically extending the idea of a feature to a collection. Basically, so if we start with some type, for instance, an int, it is very simple to see how we can extend. If we have an int, we can have a list of ints. And also, if we have an integer, we can also create a feature of that is an integer. Well, Reactive extensions composes two ideas and create something that we call observable. And in truth, observable is not a very good name. I don't like it a lot. Because the intuitive idea for an observable is a string. It's basically like a type that is going to produce elements of a type that we know of and that we are going to start processing in a synchronous way. And the nice thing is that, the process arrives in a synchronous way, and the code that we write is not much different from the code that we would write if we were working with an actual materialized code. We can do maps, we can drop stuff, we can take stuff. It is very, very simple to work with them, like in there. So basically, this method just takes an observable thing, which is like this. It drops the three first elements, takes the next 5, and then maps from the number to the string, and then prints the string. As it comes, it prints. In this specific example, the list is coming from here, from the method basic observable on top. But it will come from a user, introducing values in the console, or it can come through a socket. We can come from whatever. So yeah, quite powerful. There's a lot of stuff that you can do with these streams that you cannot do easily with other technologies. You can merge these streams, right? So here, we are merging the big nums and the small nums, and you can pipe one after the other. In this case, and since these streams are coming from local, they are treated first one, then the other. But it's possible to parallel merge those two streams as they come. So if the first stream is coming at a slower pace than the second is going to be processed first. And they're both handled as if they were the same entity. Another interesting feature in reactive extensions is that you can very easily handle error situations. Your errors in reactive extension are very simple. Here, since it's a string, each time that you pull an element from the string, you may get an error. So here, what we are doing is in a very similar method as what we had before. So basically, drop 3, take 5, and then print the number. If we get an error, if we get an exception, it's an error. If we get an error, instead of a value, we just print a -1. We put a default value. Or even we can go a bit further and say, well, when you have an error, pull from a different observable. So here, for instance, somebody that we have numbers from a cache, and we want to start reading numbers from a cache. But it may or may not be there. But here, when the numbers are no longer in the cache, we can take them from the database. So we implement the on error receive next numbers from the database. When the original observable numbers from cache fails, we will start processing from the database. No question? So it's a very cool solution. It works very well, and even though originally it was for .NET, which I don't like much, but it's a good language. But yeah, Microsoft. Now you have implementations for pretty much anything. You have reactive extensions for Java. There's I think it was. You have an extension in Scala. You have reactive extension in JavaScript. You have any language you may want to. They work pretty well, but they still are not perfect. They are for a single node. It's very difficult to move reactive extensions into more than one node. How do you implement it? It's not clear. There are some partial solutions. There are some teams that are actually working on that. But as far as I know, and the current React Conf is happening right now in San Francisco, so maybe there's something new, there's nothing to move them farther than a single node. Fault tolerance, even though you can model some errors, it can be difficult when errors compose. So, and then last, the back pressure, which is what it actually kills. That if you have a string, well, it's like a pipe, like the internet. So what do you do when you have the capability to handle what is coming through the pipe? You are processing slower than what the pipe is feeding. Well, what do you want to do? You can throw stuff away. You may say, well, let's put a key in there, because the key is bounded. You cannot put it all forever, so it's not clear. There is something called reactive strings, it was called, which is basically reactive extensions implementing back pressure. And that's a partial solution for this. And there's actually a standard for it, and it's very interesting. But I'm not going to go into that now. I'm going to talk about actors. And the actor model is something that is actually very old, although it's become quite trendy lately with ACA, but the paper for actors is from 1973. So it's not like we just discovered America. It's something that's been there for a long time. Just that maybe that right now we are in a situation where they are starting to become much more and more useful. So an actor is basically I would call it program. It's a piece of software that can communicate through messages with other actors and encapsulates state inside. The only way that you can see the state of other actors is by sending a message and expecting some reply. So the actor is a very, very, very simplified object, if you want. Just a single point of entry, mailbox, through all communication with the outside world is going to go through. And then, upon receiving each one of these messages, it's going to start processing them sequentially, one after the previous one. So, until it completely finishes processing one of the messages, it will not start with the next one. It is very important not to block in an actor, because if you block in an actor, you are not doing it for your payers. If you're not here, to be clear for an actor, it's a state machine. In fact, ACA has one of the packages is 10%, which is, I think, it's a state machine, but to actually implement implementing a state machine with actors. In actors, it's trivial. So an actor is a container for, or I say, state, which is what state I need, behavior, good, and then the actor also has permissions to do all this stuff. Mailbox, which is the way the stuff is coming in. Children, an actor can spawn as many children as it wants. Here, for instance, this actor has a receive method, which is the way that the messages come through, like mailbox. Mailbox is a class that you see here. And then when it receives a message, it just increments the counter and creates a child to which it sends it to. It's simple. And an actor can also have a supervisor thread. Well, something that I think I already said is messages. So this button is here, it's sending a message to an actor, right? And it's not blocking. You can do other stuff like ask, redirect, I'm going to go into that. So message sending is asynchronous, you don't have to wait, and the actor will completely process the message before starting with the next one. And this is very important because it frees your concurrency, your state from concurrency inside of the actor. And you see here, this counter, I'm incrementing it here. If I'm using a current integer, I'm not using a synchronize or anything. Since I'm in an actor, and I'm inside a receive method, I know that no one else has a reference to this actor. I know that that is going to be very safe by definition. So, what happens if you send a message to an actor, to a single actor of yours, and you get an exception? Well, usually, you may not care. You don't get an exception back. And why you don't get an exception back? Because in actors, there is the idea of the supervisor theory. Here's your parent, here you, here your children. But you may have a parallel hierarchy of the actor that actually know what to do in each situation. So if you throw an exception, if you are processing a message, if you are an actor, well, you are going to have it, so you are going to be distracted. Just like that. And if you want to see something different, you have to implement a supervisor strategy. So basically here, we can have a child actor that throws an exception, and the parent doesn't really care. We can implement a supervisor, and the supervisor may be notified when the children have died. Something called a death watch. It can be implemented like this. Basically, you have a reference to the actor you want to watch on, and you're going to get a message, because you're as a supervisor, you're also an actor, when an actor dies. And then you can decide what to do. You can log a message, you can restart the actor, you can do whatever you want. So something that I missed here. Is that when you're a parent actor, you can also specify a strategy to use with your children. So as a default, you will throw an exception if you want to restart. You may have something different. I'm going to go over the time, so I'm going to finish very quickly. So actors are a very good solution, and they are the solution that I tend to go for most often. But still, they have problems, and they are not small problems. First of them is that an actor is only safe when you are not sharing state. If somehow someone gets a reference to your actor and starts sharing stuff inside, well, your actor is no longer safe. And depending on if you are running on Erlang or on Naka, you are running the JVM, that may happen. It's a big problem. Another one is queue management. The mailbox is a queue that is processed sequentially. If you block, the queue grows. Even if you don't block, that queue may grow forever. So you need to think of what you are going to do about the management. And lastly, the size of the actors is actually quite big. They are not small objects. So you have to be careful about how many of them you do. And I'd like to finish with this quote by Alan Kay when he was talking about object-oriented programming. Because when I was at university, I learned about object-oriented programming, about objects being like these kind of boxes with a state inside that were communicating through messages. I remember when I started learning object-oriented programming as in Java, as in C++. and saying, well, this is method calling, it doesn't look like what they are telling me. And I go to this description of reactive programming by Alan Kay, which is only messaging, local rotation and protection and hiding on state process, and extreme late being finding all things. And it looks very, very similar to the actor model, which is it looks very interesting to me, especially after Alan Kay saying all the time that Java is not what he had in mind, C++. And with that, I'm done. So, thank you.